Here are the sample problems for Math 117 Class 9. This first one is just an exercise in interpreting weird notation. So here's the weird notation. Although we're going to do this problem by evaluating a sum, Deneen writes it as an integral. And we are integrating over just part of the sample space, the numbers 1, 2, 4, and 6, chosen from 1 through 6. And this integral tells us to calculate the expectation of the random variable x. But only over a part of the domain. So if this were evaluated over the entire sample space, we would compute the expectation of x. As it is, what we're supposed to compute is a little bit different. It means we're supposed to multiply x by the indicator function for the event 1, 2, 4, 6, and then calculate the expectation of that. Now, there are two ways of doing it. Because we know that in this case our sigma field is all possible subsets of the sample space, it's perfectly legal to sum over the domain. The technical term for this is we're using the law of the unconscious statistician. And so the way Deneen in the book gets the right answer is to say evaluate x at 1, multiply by the probability of the event 1, add on the value of x at 2 times the probability of the event 2. Note we skip over 3. We do the same thing for 4 and for 6. So now we've decrypted the notation. We know that x of 1 is 1. Probability of 1 is 1/8. X of 2 is 2 squared, or 4. The probability of 2 is 1/8. X of 4 is given to us as 5. And the probability of a 4 is 3/16. And exactly the same thing is true for 6. And you add it all up. You get 5 halves. Absolutely elementary. If we want to use the definition of expectation and comply with the spirit of this notation, we really, however, should sum over the codomain. And that means we should use the so-called canonical representation of this simple random variable and say its value 1 times the indicator function for the inverse image of 1 plus 4 times the indicator function for the subset in the domain that gives the value 4 plus, and now here's the difference. We have the value 5 times the indicator function for the set 4, 5, 6. That leads to the value 5. And although we won't need it, we probably should add on 9 times the indicator function for 3. In other words, I've done the orthodox canonical thing and written one term for each possible value of this random variable. Now when I calculate the same expectation, I have to work out first the expectation of the indicator function for 4 and 6, and that, of course, is the sum of the probabilities for 4 and 6, which is 3/16 for each, or 3/8. So now I sum over the range and say the value 1 occurs with probability 1/8, the value 4 occurs with probability 1/8, and the value 5 occurs with probability 3/8, and the answer again is 5/2. Well, I hope that's taught you something about notation, because Deneen uses this notation for the entire rest of the book, even in cases where what he writes as an integral is in fact just a very straightforward sum. Problem 2 is on a topic that's not really in Deneen, but what I want to do is to show you how to compute expectations that look initially as though they ought to be evaluated by summing an infinite series. And my example is from the game of craps. Nathan Detroit is a character in the Broadway musical Guys and Dolls, which features a lot of craps games. So I'm going to tell you how craps works and then do a calculation. Nathan is the shooter, and he rolls the pair of dice. If he rolls a 7 or 11, he wins immediately, and if you bet on him, you win immediately. If he rolls a 2, a 3, or a 12, he has crapped out and he lost the game. If he rolls anything other than 7, 11, 2, 3, or 12, he establishes a so-called point, and we're imagining he rolls a 6. That becomes his point. Now the rules of the game change. 7, which was good on the initial roll, now becomes bad. Nathan keeps rolling the dice until he either rolls a 6, in which case he wins and you get paid off, or he rolls a 7, in which case he loses and you get nothing. When you win, you get double your money back. You bet 11, you got 22. Okay, so you've placed this bet. The first roll happens, and you are called away for some reason. But there's someone with you who says, oh, I'll take over your position. How much do I need to pay you? So we have to calculate the fair price, little x, of your bet, given that Nathan has rolled a 6. Well, first things we have to calculate are the probability of the 6 and the probability of the 7. There are 5 ways of rolling 6. You can have 1-5 or 5-1. You can have 4-2 or 2-4, and you can have 3-3. So the probability of the 6 is 5/36. The probability of the 7 is a little bit bigger. It's 6/36, because you can combine a 6 and a 1 in 2 ways. You can combine 5 and 2 in 2 ways, and you can combine 4 and 3 in 2 ways. What's our partition? It's the total is a 6, the total is a 7, and everything else. So, if X is the random variable that represents your winning, and we're denoting that by little x. We can say that's payoff of 22 times the probability that he rolls a 6, and I'm going to do away with the extra squiggles here, plus your payoff of 0 if Nathan rolls a 7, plus x if he rolls something else and the game continues. Well, that's nice because it gives us an equation that we can solve for x. This probability is 1 minus the probability for a 6 minus the probability for a 7, or it's 25/36, and therefore x is equal to 22 times 5/36 plus x times 25/36, or 11/36. X is equal to 22 times 5/36, and finally x is equal to 22 times 5/36 times 36/11. In other words, it's 5/11 of 22. So your position is worth $10. If you carry out this analysis for all other possible values of the point, you can figure out your probability of winning at craps, which turns out to be slightly larger than 49.5%. Now, there are other ways to do this problem. Here, I think, is the shortest one. We think in terms of conditional probability, and we say the game ends if Nathan rolls a 6 or a 7. In other words, if the event A6, a 6, union with A7 occurs, and the probability that you win is the probability of a 6 conditioned on that event. In other words, the probability that he rolls a 6 conditioned on the fact that the game ended is the probability of the intersection of these two events. This is the definition of conditional probability, divided by the probability of the event on which we're conditioning. But the probability of the intersection of a 6 with either a 6 or a 7 is just the probability of a 6. The probability in the denominator, since these are disjoint events, is the sum of the two probabilities. So we get 5/36 over 11/36. Your probability of eventually winning is 5/11. You have a 5/11 probability of being paid $22, and again, 5/11 times 22 is equal to 10. Or there's yet a third way of doing this, by summing an infinite series. Let's work out the probability of the event that you win on roll n. Well, the probability of winning on the first roll is 5/36. The probability of winning on the second roll is that multiplied by 25/36, the probability that the first roll was inconclusive, and more generally, the probability of winning on the nth roll is the probability 2536 raised to the n minus first power, that the first n minus 1 rolls are inconclusive, multiplied by the probability of 536 that he finally rolls that 6, and therefore summing the probabilities of this countable infinity of events, we have 536 times the sum, and now I'm going to replace n minus 1 by m. I'm summing from m equals 0 to infinity 2536 to the m. So I have 536 times the sum of this geometric series, which is 1 minus the ratio, 2536. That's 536 over 1136, which again is equal to 5/11. You can follow this up on the homework to do a more complete analysis of graphs. And since the proof is rather subtle, I'm going to end this recording and put the proof into a separate file.